It's muted. So should be good now. Okay. Um, okay, so first about the assignment. So like I noticed there are like two submission portal in our Brightspace. I'm not sure what's like why that happened, but like since maybe it's like I create one portal and the professor create another one. So there are like two now, but like as long as you submitted one to like any portal, it should be cool. Should be okay. So let's go through today's problem. So we're gonna have 6 questions to do. And like first 2 of them are the bully question. So so like 2 bully question and like the other 3 gonna be easy and the last one gonna be a little bit harder. So like I strongly recommend you guys like practice the last one when you have time. Computer just lagging now. So let's do the first one. So like for all the pulley question, like when you see a pulley like this, the first thing you wanna do is like you wanna set a datum. So it's like based on what kind of like position or like what line we're gonna draw gonna measure the distance. So for this question, for example, I can set a datum right here. And if I set a datum here, I'm gonna measure the SC gonna be like this. And I'm gonna measure SP like this, and SA is not gonna change. So that is one way to set up the datum. And actually there's another way, it says like you can set up a datum at a very low, like low point on here. So like in this case, this one can be like SC and like going up all the way here can be SB. And also like SA is like this. So like it actually doesn't really matter where you set the datum, but you always want to keep things like simple and easy for doing calculation. So like I personally really like recommend you guys to set a datum like either on top or on the bottom. So it's like, for example, I'm setting here, but theoretically you can always set a datum like in the middle, like at point C, like doing this. And in this case, like maybe you want to say this one is SC and this one is SB. Like theoretically, it is possible, but like during the calculation, when we are doing the calculation about SB, it's actually a relative velocity. Like when you're doing derivative of SB is actually gonna be a relative velocity of B respect to C. So like I mean like if you set up the datum in the middle, it's gonna create a lot of like trouble or like mess. So I'm just like don't actually recommend you guys set a datum like in the middle, just like keep it simple at the top or at the bottom. So for this one, I'm just gonna set it on the top. Where like you can see those are like some fixed surface. And the next thing, so after we set a datum, the next thing we want to do is we want to find like a constant length of the rope. So like I think it's pretty easy to understand. It's like the total length of the rope is not gonna change. Like no matter how the pulley move, the total length of the rope is not gonna change. So like in this system, we can count there's one cable or like one rope in the orange color here. Okay, so there's some chat. Like I'm just nothing. So here's our first rope or cable, and the red here is the next one. So we have 2 cable in this situation, and then we're just gonna write down like what's gonna be the equation, like the relationship between the rope and those like SC and SB. And so for the orange rope, I'm gonna call it rope 1. Rope 1, and the red one is rope 2. So for rope 1, move this to the left, and I'm gonna raise the arrow here. For rope 1, the total length of rope 1, L1, is equal to, like from here, go all the way down here. So that is SB. Plus another length is from point B to point C. So from point B to point C, it's gonna be SB minus SC. So it's like we're calculating actually the distance in blue. So it's SC minus SB. And like, wanna fit them in one screen, so I'm gonna make it smaller. And like now we, like the first one SB is going down to here, and then we go up to point C, and then the rope gonna go down to point B again. So like just do another SB minus SC. So like from here, we know like the total length of the rope 1 gonna be equal to the SB, like going down and then going up and then going down. So this equation is equal to a constant value, like the length of rope 1 is not gonna change. So that's for rope 1, and then we can do the same thing for rope 2. Gonna write it in red color. So rope 2, gonna say is L2. The total length of L2 is equal to SC. So it's from point C, go all the way up to the pulley, plus SA. So it's like from the pulley to point A or to the motor here. So now we have a equation like that's the distance equation for rope 1 and rope 2. And like remember the equation we had before for calculating the velocity is velocity is equal to the first derivative of the displacement, and the acceleration is equal to the derivative of the velocity. That's something like we covered in the past 2 weeks. And in this equation, this question, we need to find the time for the load B when the load B is like 10 meters per second. So like we are giving VP is equal to 10, and then the cable is running to the motor. And then we know the acceleration of the motor or A is 3 meters per second, like we just need to find the time. So like we now need to, we now have the relationship between A and B, B and C and C and A of displacement. We just need to do this two, like finding the derivative of those to get the relationship for velocity and the acceleration. So for rope 1 also, essentially we're just gonna do the derivative on both right-hand side and left-hand side. Okay, so once we set up the equation here, like we already mentioned that the L here is a constant. So like the derivative of constant is gonna be equal to 0. So we put a 0 here, like the total length of the rope is not gonna change. So it's like it's also not going to change over time, so it's 0. And then the derivative of SB over time is the velocity at point B. So this one becomes VB plus, we can do them like separately, VB minus VC plus another VB minus VC. So just simplify everything. We can get 3 times VB minus 2 VC is equal to 0. So 3 VB is equal to 2 VC. So that is for rope 1, the velocity function for rope 1. And then we need to do the same thing for rope 2. So just finding the derivative on both sides. Then since we have L2, since L2 is another constant value, that's the total length of the second rope, it's not going to change over time. So it's 0. And the SC is actually changing over time. So that is VC plus VA. So here's another equation like relating VE, the velocity of point C and the velocity of point A. So now we have the velocity function. We just need to do this, like do the derivative again for the acceleration function. So that is going to be fairly easy. I'll keep it like 3 VB minus 2AC is equal to 0. So we're finding the derivative of 0 on the left-hand side, and the right-hand side is 3 times the derivative of VB over time minus 2 times the derivative of C over time. So the derivative of 0 is 0. And the derivative of velocity at point B is the acceleration at point B. And the velocity at point C is the acceleration at point C. So actually we're getting the same thing as before, as like this one. And just exact same procedure for the rope 2, the acceleration for rope 2. So finding the derivative of 0 is 0, and the derivative for the velocity at point C is the acceleration. So those become 0 equal to AC plus AA. And then I'm gonna make them smaller. So now we get 2 equations, the first one and the second one. Then like we got a relationship between the acceleration in point A and the acceleration for point B by these 2 equations. Yeah.
So basically, we have formulas and we find derivatives of the formulas and then do elimination. Or can you explain a bit more how to do this?
Like how to do derivative?
So, like, how does the problem work?
Okay, so like what we need, like the question was asking, okay, what's the question is asking? Yeah. So that means VB is equal to 10 meter per second. And also we need A at point A is equal to 3 meter per second square. So like we're given the acceleration at point A and we need to find the acceleration at point B. So, okay, maybe it's gonna be better to understand like we have the acceleration at point A. The next step is we find the acceleration at point B. And since like we already have the velocity at point B, we have VB. Then with the acceleration and the velocity, we can easily find out what's going to be the time for point B to reach this velocity. So we can get this one. Like, find VB is equal to what? Yeah, so like we're just like finding the velocity, finding the acceleration at point B now. Like all those equations on here are for finding the velocity, finding the acceleration at point B. Yeah. So like those are just some derivative, and from equation 1 and equation 2, we can get the relationship between the acceleration at point A and the acceleration at point B. So that would be 3 times AB is equal to 2 times AC is equal to 2 times AA. So 3 times AB is equal to 2 times AA. Now we get AB is equal to 2/3 AA. And then we know the value for AA, acceleration at point A, is 3. So that would be 2 meters per second square. So now like we finish our first step, finish our second step, and the third one is already given. We just need to find out the last step. Like we know the acceleration at point B is equal to 2 meters per second. We know the speed at point B like is equal to 10 meters per second. And like how long does it need to actually reach the speed? So the acceleration at point B is, sorry, it's not. The velocity at point B is equal to the acceleration at point B times the time t. And from here, t is equal to VB over AB. 10/2, so it's 5 seconds. So like now we know it needs 5 seconds for point B to reach 10 meters per second. Okay, does it make sense to everyone? Okay. Okay, so let's go to next one. So I'll make this layout looks a little bit better. Okay, so the second one, the question is, we know the velocity for block B is 300 millimeter per second, And we're going to determine like the first one, the question A is to find out the velocity of block A. So the first one is, what is the A? And the second and third one, they're like very similar. It's finding what's gonna be the velocity of the rope, or like what's gonna be the velocity of point C and point D. And the last one is finding the velocity of C respect to A. So that is velocity of C respect to A. Like how I remember this one is like writing the velocity first is the velocity of the first value, or like the first number is C with respect to the dash to A. So it's like we're finding this value. Then anyway, we're doing the first one first. Okay. So like we're given the velocity at point B and we're finding the velocity at point A. So we need to set up equation that only contains two value, that is VA and VB. We don't want any more like unknown or like some constant into this equation, because like if we put down something like VC or VD, we don't know what that is, and the equation gonna be like too many unknown in there and we cannot solve it. So we are given, maybe I'll write in black. We're given VB and we're looking for VA. So we need to get an equation that only contains VB and VA and VB. Like we don't want any more. So that's actually the actual idea about how we're gonna solve this one. And then we can set a datum and then like mark the distance. So like for this one, I'm gonna set a datum here. So I'm gonna say from the datum go all the way to point B is SB, and from the datum go all the way to SA is SA. So just like before, we're gonna say the total length of the rope is equal to L. But actually, I'm gonna erase those. That is the total length of the rope. So L is equal to the first one is the SB. So gonna be from here, go all the way to here, SB. And the second portion will be from SB going back to SA. So that is a SB minus SA. And then we're going back to here, point here. So we're gonna need another value. So oops. From the datum, like from this, the left-hand side of the wall to the right-hand side of the wall, it's gonna be a constant, like no matter how the A and B move or like the pulley move, the distance between these two walls is always gonna be a constant. So this one, like I'm gonna use a smaller L. So going to the right, so that is gonna be L minus SA. But that would be from here, go all the way to here. And then we're going back. Going back is another L minus SA. Okay, so are we agree on this one? So that is the basic function, or like the relationship for SA and SB. And also, like you can see from this relationship. The only unknown is gonna be the SP. Like this one, wait, we're given SP. Yeah, the only unknown is the SA. This is the unknown. And all the stuff, they're either gonna be the known condition or they're just gonna be the constant. And then we're just like before, we're gonna find the derivative on both sides. So the left-hand side is finding the derivative of a constant L. And the right-hand side, first one is the derivative of SP plus the derivative of SP minus SA over P. So next one is the actually doing the derivative. So like before, since we know the total length is a constant, the derivative of constant is 0. So we have 0 here. And the derivative of SP is the velocity of SP of point B. So it's VP plus this one. So the derivative of SP is VB plus, oh, it's a minus VA plus, so on here, the smaller L, remember the smaller L is the distance between the left-hand wall and the right-hand wall. So it's also a constant. So L is this one, like the distance between two walls. So they're constant. It is constant. So it's gonna be 0 here. And it's gonna be a minus VA, like doing the derivative of SA. And the same thing. So we can simplify this one. We get 2 times VB minus 3 times VA is equal to 0. And the question is asking for VA. So VA is equal to 2 over 3 VB. That is equal to 2 over 3 times the value for VB. The value for VB is here is given 300 millimeter per second. 300. So it's 200 millimeter per second. Okay, so that is the first question. Okay, so next one, we're going to find the velocity of portion C on the cable. So it's gonna be a very small, very little difference between question A and B. Like question A, we're finding the velocity of a block like this. The block is actually attached to a pulley, and a pulley is attached to the cable. But in question B, we're finding the velocity of point C, and point C is right on the cable. So it's like something attached to a pulley and a pulley attached to a table, not table, cable. And the next one is like, second one is like directly connected to the cable. So for this one, we can actually simplify the model here to get the question like a little bit easier to understand. So we're gonna redraw the model here. So the rope gonna start from here. So that is gonna be the same. From here, connecting to a pulley here, and the pulley here is connected to point B. And actually when it reach point C, so like we're looking for the velocity at point C here, we're looking for VC here. we can just assume that this point is attached to like a block or like anything, point C, and we're looking for the velocity of this block. So like the system, like the complicated system can be simplified to something like this. Like VB is given. And we're just looking for VC. Like we don't need to worry about the cable for the rest, since like we're only calculating the velocity at point C, and it's right on the cable. So it's like when you have a question that is asking the velocity of like a point on the cable, we can always like simplify the model like this. So then it's going to be easier. It's also going to be the total length of the cable will be equal to, like everything going to be the same. From here is SP, from here to here is SC. Going to be equal to SB plus SP minus SC. And then we find the derivative on both sides. So again, this one gonna be 0 since L is a constant. So that means the rope, the total length of the rope from this point go all the way to point C is a constant. So this one becomes a 0, and this one is a VB. And the last one is VB minus VC. So what we have on here is 2 times VB is equal to VC. Then the VB is a given value. It's 2 times, what is VB? 300. So that is 600 millimeter per second. Okay, so that is for question B, part B. And then part C is very similar to part B. So part C, instead of finding velocity at point C, we're finding the velocity at point D. So we're finding the velocity on here. So again, we're just gonna redraw the model, simplify everything. We have the rope starting here and gonna going to point B and going back. So this one is point B. And going back, we have point A over here. And that is the point D we're going to find. So all the notation are the same, SP and SA and SD. They're all starting from the datum on the left. So the same thing, the total length of the rope from the wall from here go all the way to point D is a constant. So it's gonna be equal to SP plus SP minus SA. Then back on here and then plus SD minus SA. And then just like before, we're gonna do the derivative on both sides. So the derivative of a constant is 0, and the derivative of SB is VB. The derivative of SB is VB, and it's a minus VA plus VD minus VA. So essentially, we're going to have 0 equal to 2 times VB minus 2 times VA plus VD. So VD is going to be equal to 2 times VA minus 2 times VB. And before, like the VB is given, and in our part A, we already find the value for VA. Then we can just plug in a number on here. So VA is 200, what? VA is 200 millimeter per second. So that is 2 times 200 minus 2 times 300. Final answer is going to be negative 200 millimeter per second. So like the negative sign here, that means the direction is in the another direction, like it's in the opposite direction with respect to point B. So like you can go back to the question to check if the negative sign actually makes sense. Okay, so that is part B and C. They're actually using the same idea. It's like you simplify the model and then you just like do the same thing as before. Okay, are we all good on like on those, especially the model like simplification? Okay, then there's the last one. This is the last one. We're going to find the relative velocity of portion C with respect to A. So we're finding the relative velocity of C with respect to A. And there's a kind of like a formula or the equation you want to memorize. It's like VC over A is equal to VC minus VA. So actually how I remember that is pretty straightforward. So it's like VC dash A is equal to VC, dash become a minus sign, VA. So you don't have to like memorize something else. It's like for me, this one is the easiest way for me to remember that. And then we already find what is VC, what is VA. We just need to plug in a number there. So VC is 600. VA is 200. So 6 minus 2 is 4. So that is for part D. So another thing keep in mind is that when you're doing some relative velocity, you want to keep in mind like you want to check that, like double check the sign or the direction of the velocity when we're actually doing the math. So like for this one, we're finding the velocity, finding the relative velocity of C respect to A. But what if the question is asking finding the relative velocity of C over D? So that is VC minus VD. So in this case, VC is going to be the same, but VD, you have to remember VD is in another direction. So you need to include the minus sign over here to our equation here. So like you need to put the minus sign here, and the actual number is actually going to be equal to 800 millimeter per second. If you forget this one, you're gonna get 400, and that is not correct. Okay, so that is for question 2. So let's move on to question 3. So in question 3, we have two vehicles. One is moving, like both are moving up, but like in different direction. And we're given the velocity for both vehicle, and also the acceleration is also given. So for point A, or like the vehicle A is 4 meters per second square, it's accelerating, increasing speed, so it's accelerating. So that means A is equal to 4 meters per second square. And the speed of B, like the acceleration for point B, is actually decreasing. So we can either write the AB is equal to -3 meters per second square, or like just say the direction is in the opposite way, and the magnitude of the acceleration is also 3 meters per second square. So like I personally prefer the last one because I don't really like the negative value. So I'm going to do it like this. And the question is asking for the relative velocity and acceleration of B respect to A. So again, it's like we're going to find the velocity of relative velocity of B respect to A. So going to be B dash A. And the equation for this one is pretty easy, like VB, just copy down VB, and a dash become like a minus and VA. So the same thing for the acceleration. Okay, so these two values are the final answer we're looking for. So the first step we want to do is for the velocity, we're just going to find out what is VB and what is VA. And in this equation, since we have a 2D equation, we have a 2D problem. So this one is, like we call it a 2D problem because it's like, it's not moving in the same direction. Like normally, like those pulley system, like those pulley question, they're either moving down or moving up. So those called the like 1D question. But this one, like you actually have an angle, you're moving like on a plane. So it's a 2D problem. In this kind of 2D problem, we sometimes like we use the Cartesian vector. So we're gonna apply the Cartesian vector over here. And for the Cartesian vector, like for the coordinate system, we call the horizontal direction is X, vertical direction is Y. But in this case, since like we're just like gonna have a like notation for the direction of the velocity, we just use I and J. So for horizontal, we usually use I. For the vertical, we usually use J. So I mean, don't be scared about the I and J, they're just like some direction. Because like I remember when I took this course, when I first see like a lot of I and J, I was so scared. So we're gonna find what is VA and what is VB. So VA is given on here is pointing upwards, and it's 40 meters per second. So since it's pointing upward, it doesn't have any component on the horizontal. It doesn't have any speed on the horizontal component. So it's going to be 0, 0 I plus the J direction is pointing up. So it's 40J. So that is for VA. And for VB, we're gonna use some trigonometry. So like, just gonna redraw the triangle here. So this one is the VP we have. And we're gonna project the velocity vector onto our horizontal and the vertical plane. So in the J direction, it'll be something like this. Just gonna project VP on here, and gonna do the same thing for the horizontal direction. And always remember, like going to the right is the positive direction, going up is also the positive direction. So for VP, we can see the I component is a negative value. So it's gonna be, okay, so this one is theta, how big is theta? 30 degrees. So for VP is equal to negative VP sine theta in I direction. So the negative sign here means the direction is pointing to the left. And also do the same thing for the J direction. So J direction is pointing up, so you have a positive sign here. So that is for VA and VB. You just need to plug in a number to find out what's going to be the actual value for VB, and that is going to be negative 30 sine 30 degree in I direction plus 30 cosine 30 degree in J direction. So VB is equal to negative 15 in I direction plus 15 square root of 3 in J direction. So here we have equation for velocity A, and we have the number for velocity B. You can just plug in everything into this equation to find out the relative velocity. So the relative velocity VB over A is equal to VB minus VA. Okay, so like when the velocity is written in the vector form, and when you're doing the summation, like when you're doing the math calculation, you only want like the I component calculating with the I component and J component calculating with the J component. So in this one, VB, that is 15I plus 15 square root of 3, J minus 0, I minus 40, J. So I go with I and J go with J. So 15 minus 0 is minus 15. I, and for the J, that is 15 square root of 3 minus 40. J. So like this one, you can use a calculator to do that. That is negative 14.02 J. Okay, so that is the relative velocity of B respect to A in vector form. So like sometimes, like for myself, I think it's okay to have the final answer like this. But I mean, sometimes in the exam, the professor or the question will ask you to change the format from the vector form to like the normal form. So what you need to do is finding the magnitude and also the direction of the velocity. So the magnitude is pretty easy. Well, they're both pretty easy. You just need to finding the magnitude. So here's the magnitude, and then the next one is the direction. So theta is equal to tangent to the power of -1 of the formula will be J over I. Like you can memorize that, or you can just derive that based on a triangle. So what we have on J is -14.2. What we have on I is -15. And this one is equal to 43.06. So you can finally write the velocity of B respect to A is equal to 20.5 meter per second in magnitude with an angle that is 43.06 degree. So that is the procedure to find the relative velocity. And for the acceleration, the idea is the same, but we just need to consider, yes?
For the direction, is it always J over I?
Yeah.
Always?
Yeah. Or like, if you're not sure about the direction, you can just like draw this one on the coordinate system. So it's like in the I direction, it's a negative value, so it's like -15, approximately gonna be here. And the J direction is also a negative value, so like should be something like this. So now you can easily see like what's gonna be the direction.
Okay.
Okay, what I want to do next? Oh. But yeah, we're doing the acceleration now. So that is for the velocity. And for the acceleration is the same idea. So the acceleration for A is given on here, is given here. It's 4 meters per second square pointing up. So that's gonna be 0 on the I component again, plus 4 on J component. So that is the acceleration for vehicle A. But the acceleration for the vehicle B is gonna be a little complicated since vehicle B first is decelerating, so it has a tangential acceleration, and also it's moving on a curve, so it's like moving on a circle. So we have another normal direction, like normal acceleration. So the acceleration B actually have two components. One is the acceleration in the tangential component, another is the acceleration in the normal component. Like for me, how I understand, like for the particle moving on a curve has two components, like acceleration component is, so for anything on a curve, like the speed, if the speed is changing, there must be a acceleration to change the magnitude of the speed. So the tangential acceleration is for change the magnitude of the speed. And also since the car is moving on a curve, so like the direction of the speed is also changing. So it's like we need another acceleration to change the direction of the speed. So like the normal direction, like the acceleration in the normal direction, it won't change the magnitude of the speed. It only change the direction of the speed. So this one change the direction of speed. So it's like the speed have two components, the magnitude and the direction. So you need two acceleration to change that. I mean, that is how I understand or like how I memorize. I need to have two components, like two acceleration component. Okay, so back to our question here. It has a tangential component and the normal component. And the tangential component is pretty easy. It's just like written on here, 3 meters per second square, pointing like downwards. So, okay, I'm gonna move this one to another position, and then we're gonna draw the diagram for that. So for the tangential acceleration, it's actually pointing downwards. And also like we're gonna project this acceleration into I and J plane also. This one is I, this one is J. And in I, gonna be this component. In J, gonna be this component. And also from this graph, you can see that we're gonna have a positive value on I component and we're gonna have a negative value on J component. So gonna have a positive for I, and that is 3 times, this is cosine. So that is 3 times sine theta. In I component, check. Sine, yep. So it's going to be a positive 3 times sine theta in I component and minus 3 times cosine theta in J component. And those are about the tangential acceleration. And the next one is the normal acceleration. The normal acceleration. So it's a plus. And the normal acceleration is always going to be perpendicular to the tangential acceleration. And it's always going to be pointing directly to the center of the curvature or like. So the normal acceleration will be pointing this way, and they're always going to be perpendicular. So we have the same theta angle on here. And like again, it's going to be a I direction and going to be a J direction. And also on the graph, we can see both I and J going to be a negative value. So I is a negative value and J is also a negative value. And make this one smaller. There is another equation we need to use is AN is equal to velocity squared over R. So I'm gonna just integrate this equation into our full equation. So for AN gonna be V squared like, what is V? It's 30 squared over R. R is also given as 200 meters. And then theta is here, like project this one onto here, gonna be cosine theta in I component. And also a minus sign since like the direction is pointing downwards. So it's gonna be 30 to the power of 2 over 200 times sine theta in J direction. So here I have everything, just need to plug in theta equals 30 degrees and then use a calculator to get the answer. Oops. So that is negative 2.3971 I and minus 4.8481 in J. So here we have AB and AA. Then the relative velocity is same as the relative, the relative acceleration is same as the relative velocity. So like remember it's gonna be AB and dash is a minus AA. So just gonna copy everything from above, I direction minus J direction, and the A is 0 and 4. So it's minus 0 I and minus 4 J. So I minus 8.8481 J. Also, like this is in the vector form. If you want to write it in the like normal form, we're just finding the magnitude and also the direction. Oops. So also like, as we mentioned before, if you're not too sure about like what's gonna be this angle pointing towards, you just need to draw a coordinate system and like put down the vector form there. So one is like around 2 and another is around 8. So gonna be a point on here. Then your angle is like pointing this one, and this one is gonna be the 74.8 degree, like pointing this direction. Okay, so that is everything for question 3. I'm actually gonna charge my computer. Okay, are we all good on this one? Just a lot of math. And the idea is not that bad. So next one is also like very easy. I guess it's just like a high school question, but like now we are going to work on the empirical units. So like, I'm not sure if you're familiar with the empirical units in your high school, because like in my high school, we only deal with the SI units, like meter, like those kind of stuff, and we like meter, kilogram. So it's like when I first dealing with those British or like empirical units, I have like really hard time. So let's read out this question. So the rocket itself is, the weight of the rocket is 0.2 pound. And it's gonna take off vertically from the rest. From the rest means like velocity at the very beginning is 0, and when time is equal to 0, and the thrust is equal to 2 pounds for 1 second. So like can draw a diagram like this. The total height is gonna be h. So it's like the rocket gonna be launched from here, go all the way up, and that is the total height. And there are 2 sections here. The first one, we're gonna call it H1, and the time is going to be T1, and T1 is 1 second is given. And the second one is the H2. So in the H2, in this area, the thrust is 0. So that means the acceleration is just the gravitational acceleration. And the time T2 is an unknown value. We're gonna need to find that. So we're looking for the maximum height h and also the time required to reach that. So that means we need to find the h equal to h1 plus h2 and t equal to t1 plus t2. So first we need to know the acceleration. To know the acceleration, we just use the Newton's second law. The resultant force, or the sum of the force, is equal to the mass of the object, in this case the rocket, times the acceleration. And when the rocket just took off, I'm gonna draw a rocket like the free body diagram. It's gonna have a weight and it's gonna have a thrust. So the resultant force is gonna be thrust minus weight. That is equal to MA. So the thrust is given is 2 pounds, and the weight is also given is 0.2. And it's equal to the mass of the rockets times the acceleration. So the mass on here, we need to calculate that from the weights. So it's like when we're having a question in the SI units, usually the weight is given in kilogram or in gram, that is like a mass unit. But like in the empirical units question, the weight is always given in force. So we need to convert, it's not convert, like we need to calculate the actual mass from the force. So there's an actual step to calculate the mass. So mass is, or like the weight is equal to the mass times the gravitational acceleration. And from this equation, mass is equal to W over G. So that is equal to 0.2 pounds. And the gravitational acceleration in the empirical units is 32.2. So like this number, you have to memorize that. Like usually in an exam, if you don't remember that, probably they won't give it to you. And if you like, if your professor is like not a nice guy, he won't tell you, and you're just like kind of screw up there. So this one, you need to memorize that. Like there was for like, actually many times for me, like when I'm taking exam and I noticed that there's like a British units or empirical units, and I just forgot this number. So like I kind of like screw up the whole question. So it's actually a lesson learned from me. I'm just telling you guys, need to memorize this number. Okay, so 0.2 over 32.2. It's a number. How big is that? Anyway, it's a number. I don't have a calculator now, so. And actually the point is the mass unit in the empirical unit system is slug. So when you're using the formula that has a mass and you're doing with the empirical units, you always want to use slug as the mass. You don't want to use like anything else. It's going to be incorrect. So you want to change everything to slug when you're dealing with the mass. So like this one is equal to the question mark. I don't have a calculator now, but you can easily find that. So 0.2 over 32.2. So everything is set up. We just need to isolate A and find out the value for A. Times. Okay, it's 161, I guess. It's written there. So we have the acceleration now. And since we have the acceleration in the first region, we can calculate the height of the first region. So like writing down the basic equation, the displacement is equal to the initial velocity times t plus half a t squared. And in our scenario, the displacement is h1 and the initial velocity is 0. 0 times t is also 0. I'm not gonna write it there. So it's half acceleration, we have it here, and t squared. And t we are given is 1 second. So that is half 289.8 times 1 to the power of 2. And we have 144.9 feet. And also we gonna find the velocity when the rocket turn off its engine, or like when the thrust is 0. So velocity is also equal to a times the time. And that is just 289.8 feet per second. So now we have the h1 value here, it's calculated here, and then we need to just calculate its h2 and v2, I mean t2. So for finding the h2, there's an easy way. So like remember the basic equation we have is the final velocity square root of final velocity minus the square root of the initial velocity is equal to 2 times the acceleration times the displacement. So in our case, the final velocity is 0, because you can imagine when the rockets like going all the way up, when they reach the highest altitude, like the velocity is going to be 0. It's kind of like gonna drop down. So like the velocity at that moment is going to be 0. So the final velocity is a 0, and the initial velocity, we already find it over here. This one. (289.8 to the power of 2 is equal to 2 times. So the acceleration in this case, like the thrust doesn't exist anymore. So the acceleration is just the gravity. So that is a negative. So who want to say that number? No, it's in empirical units. Yeah, but we're in feet per second square. Yeah, so that is the 32.2 I was mentioned about. This one. It's like, I'm just like you. It's like when I'm doing exam, it's like, oh, it's gonna be 9.8. And when I put a 9.8 there, I realize it's in like SI units. It's not gonna work. Then I'm like stuck there. So it's 32.2 times H2. And then you can solve for H2. What is this? It's going to be 1304.1 feet. Okay, so we have H2 and the final H is equal to H1 plus H2. So it's 144.9 plus 1304.1. That is 1449. Those are too big. Make them smaller, going up a little bit. Okay, so that is for the height, and for the time, it's also going to be super easy since we have the final velocity and we have the initial velocity. So again, so the final velocity is equal to initial velocity plus AT, and the final velocity is 0. initial velocity is 289.8, and the acceleration is 32.2 times time t. Then we can solve for t, that is 9 seconds. So the total time is the time with the thrust plus the time without the thrust. So it's 1 plus 9 is 10 seconds. Yeah, so that is the whole problem. So I feel it should be pretty straightforward. The only thing is like, remember this number, remember this number. Okay, so we move to next one. So this one, we're going to determine the maximum speed of a vehicle that is starting from the rest all the way to 60 meters per second. So like what's gonna be the velocity when a car is moving from 0 to 60 meter? And we are given the friction coefficient of the tire and the road, that is 0.8. And we also have the weight distribution of the car. So we have 60% of the weight is at the front and 40% of the weight is at the rear. Also, like the first one, we are going to find out the maximum velocity if the car is an all-wheel drive car or a four-wheel drive car. And the second one is a front wheel, and the third one is a rear wheel. So like for this one, first thing, we always need to draw a free body diagram. So I'm just drawing a car. Mhm. Okay, like this. And then it says 60% of the weight is on the front, 40% of the weight is at the back. And for the wheel, so let's say the front wheel, we have F1, like the friction for the front wheel is F1. The friction for the rear wheel is F2. And they all have the same friction coefficient. Mu, that is equal to 0.8. So when the car is a four-wheel drive car, we're gonna first apply the Newton's second law, F equal to ma. And the left-hand side, the resultant force is equal to F1 plus F2, because for a four-wheel drive car, it's like both front wheel and the rear wheel gonna provide some power, so it's gonna be F1 plus F2. So for F1, that is equal to mu times weight of the front. So it's gonna be 60% of the weight. So this one is for F1, and then plus F2, that is going to be the friction coefficient times 40% of the weight for F2. So like I'm just gonna open those like plug in those number. Friction coefficient we have is 0.8 times 0.6 times weight is equal to mass times the gravitational acceleration plus friction coefficient 0.8 times 0.4 times mg. And that is like actually equal to 0.8 times 0.6 plus 0.4 mg. So 0.6 is from the front view and 0.4 is from the rear view. So like from here, you can notice that if the car is a four-wheel drive, the weight distribution is not going to be that better. So that is for the resultant force. Oops. And then the resultant force is going to be equal to MA, like the Newton's third law, Newton's second law. So we have 0.8 times 0.6 plus 0.4, that is 1 times m times 3 is equal to m times a. Then you can see the mass can cancel out, and a acceleration a is equal to 0.8 times 1 times the gravitational acceleration. In this case, we're working with the okay, the unit doesn't really matter, so just go with the SI units. And then that is equal to 7.848 meter per second square. So now we have the acceleration, and we're going to calculate the time when the car moves 60 meters. So again, we're going to use the formula, use this formula. The final velocity minus the square root, no, the power of the final velocity minus the initial velocity to the power of 2 is equal to 2 times a times s. And the final velocity is the one we're looking for. The initial velocity is starting from the rest. So this one is 0. Equal to 2 times the acceleration is over here, 7.848 times s. So it's in the question it says 60 meters. So that is a given value, 60. And then VT, you can just like find them, use a calculator, 30.69 meter per second. Okay, so that is when this car is a all-wheel drive car. Then let's go to the next one. When the car is a front-wheel drive. And this car is cheaper, it's a front-wheel drive car. So the Newton's second law is not going to change. But the resultant force in this case, since it's only a front-wheel drive, so it doesn't have any power on the rear wheel. So like in our free body diagram over here, the F2 gonna be 0 in this case. So the resultant force is just gonna be equal to F1. And then we know F1 is equal to friction coefficient times the 60% of the weight is at the front times mg. So we have 0.8 times 0.6 times m times g equal to m times a. So in this case, the acceleration will be equal to 0.8 times 0.6 times 9.81. And then use a calculator, you can see the acceleration is equal to 4.709 meter per second square. Then we just need to repeat what we did for part 8 to find out the final value. T and this one goes to 0. Final velocity is the unknown. And then so for the final velocity is 23.77 meters per second. Okay, so part C, when the car is a rear wheel drive, so only the rear wheel can provide some power. So the resultant force in this case is just gonna be F2. And the F2 gonna be equal to, or like everything gonna be equal to the friction coefficient times 40% of the weight of the vehicle and is equal to MA. So MA equal to mu times 40% of the weight. The acceleration is equal to mu times 0.4 times the gravity. So A is equal to 0. What is mu? 0.8 times 0.4 times 9.81. And the acceleration in this case is going to be equal to 3.139 meter per second square. So I have the acceleration and then just again. So it's 0 again. And then Vt will be 19.41 meter per second. Okay, so that is for this question. So let's go to the last one. So this one is going to be the most complicated one. So we have two blocks here, like M1 and M2. So we're going to determine the range of the force P. So force P, we're gonna have like a minimum value and we're gonna have a maximum value. We're gonna find out what's gonna be the range for P. So where when the P applied to the car or the M1 here, the block M2 is not gonna move. So M2 is not gonna slip. Yeah, M2 on the car here is not gonna slip. So for the block or for the M2 to sleep, there's only two cases. One is the block gonna sleeping up, another one is the block is gonna sleeping down. So there are like two cases. Two cases for M2 to, or I'm gonna say to move. So the first case is M2 will tend to sleep up or to move upwards. So this will only happen when P is like a very big number. So it's like, just imagine when the car M1 is moving so fast, it's moving like super fast, then M2 might have like very less friction to keep it like in place. So like in this case, the M2 gonna go up. So like in this case, that means P is very big. So when P is very big, we can definitely find like the biggest value for P. P max is equal to a value. So that is the first case scenario where the block M2 is moving upwards. And the second case scenario is that M2 will actually go down. So for M2 to move downwards, it can only be like the car is moving very slow or like the P is very slow. I mean, the P is very small. So like in this case, going back to our drawing here, there are actually gonna be two cases again. So like we need to decide, or like we need to, we need to analyze is like when P is 0, that means when the whole system is not moving, would the block actually dropping down? If that is, like if the whole system is not moving, the block is not gonna drop down, then we can easily find out P min is equal to 0. But if the angle on here is not small enough for the M2 to dropping down, we definitely gonna calculate a P minimum. So it's about the like a critical angle, or another way to think about it is like you can imagine it's not 20 degrees, it's like 5 degrees. So it's like you have a very flat surface. The P, like in this case, no matter how heavy the M2 is, it's just not gonna going down. So like we need to find a critical value, like a critical angle value for the mass 2 to dropping down. So we need to find a create on a critical angle, the block M2 will move downward and the So here we need to find that critical value for the M2 to actually dropping down. So in order to find that, we're just making an assumption. So like, let's say assume M2 not moving down. And the system is not moving. It's also not moving. So in this case, you can draw the free body diagram for the block. Like in this case, everything gonna be perfectly balanced. We're gonna have a gravity, we're gonna have a supporting force, and we're gonna have a friction. Since the block is not moving, then in this direction, like in the dashed line, the force should be like perfectly balanced. So here's the theta. So we have the weight, like this one is mg, or the weight, times sine theta, which is on here, will be equal to F, the friction. And we know the friction is equal to the friction coefficient times the supporting force. And we also know the supporting force is equal to mg mu times mg cosine theta. So like we're just draw the free body diagram and find out the force balance inside this free body diagram, and then just listing everything with the theta on here. And then we can just try to isolate the theta. So putting the theta on the left hand side, we have sine theta over cosine theta is equal to mu, because the mg is canceling itself. So sine theta over cosine theta is tangent theta. Is equal to mu, and theta in this case, actually I should say theta c. That means the critical theta, critical angle, is equal to tangent to the power of -1 mu. And then we can plug in the number. In this question, mu is given, like we need to use the static mu. This one is for the moving, like when the block is actually moving, the friction coefficient is at 0.25. But since we don't want it to move, so like we need to use the static friction coefficient. So it's 0.3. And then we're gonna plug in the 0.3 into here. Then you'll find out the critical angle is equal to 16.7 degrees. So we find out this angle. And what does this one mean? Is when angle of the slope is smaller than theta critical, that is 16.7 degrees. No matter what, the M2 will not move downward. So that is the critical angle. Like for our system, if the angle is less than this number, the block is not gonna moving down. So like if our angle is smaller than 16.7, we can just say the P minimum is equal to 0. But we know that in our question, you already say our angle is 20 degrees. So the decision or like the result from this one is our actual angle is equal to 20 degrees, which is bigger than our critical angle, that is 16.7 degrees. So that means we need to get a car move to stop the M2 from sliding down. Okay, so does those make sense to everyone? Okay, let's continue. So now we already know that we need to get a car move to stop the block from moving down. Then we can say we need to find out a value for P mean. So let's go back to draw the free body diagram. When like now we'll consider M1 and M2 as the whole body. So when they're a whole body, when the P is applying here, it's gonna be a acceleration, and this acceleration is gonna be the same for M1, for both M1 and M2. So this acceleration is same for both M1 and M2. Since M1 is not moving, then we can just make the free body diagram for M2 directly, individually. So there are also going to be two cases. One is the block M2 tend to move down. And the second situation is block M2 tend to move up. Because like in both cases, the free body diagram is not going to be exact same. So when the thing try to move down, we will have a mg pointing downward. It's not going to change. And also like a supporting force is not going to change. Since this one is trying to move downward, the friction is like a force that is like preventing the object from moving. So if it's tend to move down, then the friction will be pointing up to prevent the object from moving. And the free body diagram for the blocks that tend to move up is just going to be the opposite way. Can be like this. Okay, so let's follow the first case scenario first. So now like go back to our original requirement is like we need to find out what is going to be the acceleration A. Like we need to find this value. We need to, this is the unknown we need to looking for. We're looking for. So from here we can just write down the force balance and the weight balance. And then we can solve for A here. So we know the friction will be equal to, okay, let's not doing that. So let's do this. So like, we know the car, like the block is not moving up or downwards. So that means in the y direction, the resultant force gonna be equal to 0. And also for the x direction, we know like the object is moving to the right with the acceleration equal to a, and the a is the one like we're looking for. So fx is equal to ma, and then let me see. We just need to project those force to like our x and y axis, and then just like you can list some like equation. So in the y direction, everything equals 0. So we have negative mg plus n times wait, theta is okay, theta is actually here, plus cosine, oh, theta is here, sorry. So in the y direction, here I'm like listing for the y direction. The force in y direction is the negative mg plus n times cosine theta plus the friction times sine theta, and they're equal to 0. So it's from this relationship. So like all the force in y direction, they need to be perfectly balanced. So they're equal to 0. And then let's do the horizontal direction in the x direction. So that would be negative friction times sine theta plus n sine theta is equal to ma. So that means all the force in the x direction need to be equal to ma. That is like the Newton's second law. So here we have two equations, but we have one unknown. We have use another color. We have one unknown. We have two unknown, and we have three unknown. Like we only have two equations, but we have three unknowns. So we need to find another equation to make the matrix balanced. So another one is we actually know the relationship between the friction and the supporting force N. So, well, actually F is equal to the static friction coefficient times N. So that is going to be our third equation. So in this case, we have three equations and we have three unknown. So three equations and three unknown, we can solve for F, N, and A. And the math is actually kind of ugly, so I'll show you how I solve it. So they're just like math. You can just like use any method you like to solve it. Like I'm just so like I'm just showing you guys how I actually solve it. So well, actually, does everyone agree with the formula, like the matrix here we just set up? Okay, great. So from the first equation, we can have mg is equal to n cosine theta plus f sine theta. And then we can isolate for n. Then we can get n is equal to mg minus f sine theta over cosine theta, like just isolating for n. And from the second equation, like simplify everything, we can get a is equal to, well, actually, I just rewrite it. Then we're gonna plug in the unknown here to the n inside here. So that is what I mean by the math is gonna be so ugly here. So after we plug in, MA gonna be equal to mg minus f sine theta over cosine theta times sine theta minus f cosine theta. And then I'm just gonna times cosine theta on both sides. So on the left hand side, you have ma cosine theta is equal to mg minus f sine theta square minus f cosine theta square. And we're gonna put like isolated for f, or like put f out, and a cosine theta will be equal to g. I'm actually missing a sine theta on here. Sine square theta plus cosine. Okay, so from your high school math, you need to remember sine square theta plus cosine square theta is equal to 1. So this thing goes to 1. So we have ma cosine theta is equal to mg sine theta minus f. So that we're gonna have f is equal to m times g sine theta minus a cosine theta. So we found for f, and then we're just gonna plug in f into this thing. We're gonna plug in f into this thing to get n. So 1, 2, 3. So let's say this one is 4. Plug in to equation 4. So n will be equal to mg minus mg sine theta minus a cosine theta. Cosine theta, 1 over cosine theta. And then I'm gonna open the bracket. Wait, think I missed something here. Mg minus, well, I'll just write those things again. Minus f that is g sine theta minus a cosine theta times sine theta. Okay, I'm missing the sine theta here. And everything times 1 over cosine theta. And then, yeah, I'm putting the sine theta and m inside this bracket. So that is mg minus mg sine squared theta minus ma sine theta cosine theta. Bracket everything times 1 over cosine theta. So on here, the things like you need to notice that mg minus mg sine squared theta is equal to mg times 1 minus sine squared theta and minus the rest. So 1 minus sine squared theta is equal to cosine squared theta. That is mg cosine squared theta minus ma sine theta cosine theta times 1 over cosine theta. And then you can see the cosine theta can cancel out. So eventually you have mg cosine theta minus ma sine theta. Okay, I think I made a mistake. Yeah, so like here, when I open the bracket, the negative sign here actually goes to positive. So they are positive. So like that's what I mean by the math is so ugly here, and it's very easy to make a mistake like this. But essentially we get n is equal to this one and f is equal to this one, and then we're just gonna use our third equation, is this one, to find out a. So our third equation is f equal to friction coefficient times n, and on the right hand side is mu times m times like those kind of things. Those things. And the left hand side is the f, which is the value or the equation here. This one. Let me see. Yep. G sine theta minus a cosine theta. So like you can see the mass gonna cancel out. So left hand side is G sine theta minus a cosine theta. Right hand side is mu G cosine theta plus mu a sine theta. Then we just isolate for a, and then a is equal to G times sine theta minus mu cosine theta over cosine theta plus mu sine theta. Okay, so we finally have an acceleration here. And this acceleration, like remember, this case scenario is when the block is tend to sliding down. So what we are finding is the minimum acceleration. So that is the A minimum. And the corresponding p-value to the minimum acceleration is the minimum p. So the minimum p can be easily obtained. So p minimum is just going to be equal to m1 plus m2, since like it's going to be the mass of the car and the mass of the block. So it's m1 plus m2 times A minimum. And then you just like plug in a number to calculate for the A minimum. So this one is G and sine 20 minus 0.3 times cosine 20. Cosine 20 plus 0.3 times sine 20. And this equal to 0.0577G. So back to here is 0.0577G. I'm gonna put a G at the back. So like when you're reviewing this, it's not gonna be a 9. M1 plus M2 G. So that is a minimum. And then we're just gonna repeat the whole process again to find the maximum. Ooh, so for the maximum, like the resultant force in the y direction, also the same 0. The resultant force in the x direction is equal to ma. Like the only thing gonna change is the equation on here, since like the friction F is actually pointing downwards. So we're gonna have from the Fy equal to 0, from this one we can get, I'm just gonna write it down. Negative mg, that is like y and x component. Negative mg is like pointing down. Plus n times cosine theta. This is theta, so cosine theta is like what? No, that one is not sine. Okay, like I always mess up with the angle. Yeah, this one's theta. N times cosine theta and plus f sine theta is equal to 0. That is all the force in y direction is 0, and all the force in x direction is equal to ma. So that is f cosine theta plus n sine theta is equal to MA. So like you can compare the thing we have on the right hand side and the left hand side. We're going to make this one smaller. So you'll notice like the only difference is the sign for f is actually changed. Well, this one is actually a negative sign. So it's negative f. So see, like here we have positive and here we have negative, but when in our previous case, we have a negative sign here, then we have a positive sign here. So it's like just the sign gonna be the opposites, but everything else is gonna be the same. So again, this is our first equation, and then this is our second equation. And then third equation is F equal to friction coefficient times the supporting force. The third equation, and also third unknown, that is our F is an unknown, our acceleration is an unknown, and our supporting force is the last unknown. And then just like so for this equation again, this matrix again. And well, I mean, if you want to practice that, you can do that at home, but I already did that last night. It took me like 1 hour. So the answer is kind of like pretty similar. We just like reverse the sign, like the negative become positive and positive become the negative. So that is for F and that is for N. Plus A sine theta. And then you're just gonna plug in into here, the third equation, mu N. So right hand side is mu times and G cosine theta plus A sine theta. And the left hand side, that would be negative G sine theta plus A cosine theta. And then we just isolate it for A, and also again here the mass can be canceled out. So A will be equal to mu G cosine theta plus G sine theta, and the denominator is cosine theta minus mu sine theta. So that is for the maximum acceleration. And this one, you're just gonna plug in a number. And you can get cosine 20 degree minus 0.3 times sine 20 degree. And above there is 0.3 times cosine 20 degree plus mu what? Oh, sine 20 degree. And that is equal to 0.745 G. So the P max will be equal to M1 plus M2 times A, acceleration A max. So that is equal to 0.745 M1 plus M2 G. So that is for maximum P. So eventually you just say P should be between the P max and the P minimum. So that would be between 0.745 M1 plus M2, 3, and 0.0577 M1 plus M2, 3. Okay, and I'll just make note that this is J is not 9. So when you're taking like take a look at my notes like later, you won't see this one as a G. Okay, so that is everything. Oh. Any questions? So I'll stop the recording here.